Right, let's get started. So thank you for joining. So this is for Chemistry Paper 1 for your exam tomorrow. So just like the biology session that I did as well, I'll be going over some past questions. And I'll also be going over some content as well, but not covering all content, but I'll try to do as much as I possibly can with this time we've got. And after, I'll get the recording out to you as well, and I'll get all these notes to you as well. And the chat's also open as well. So if you've got any questions as I'm going along, just drop them in the chat. So let's get started. So the main thing, I guess, with Chemistry Paper 1 is understanding the periodic table as much as possible and using it to your advantage since you're given it in the exam. So as soon as you get into the exam tomorrow, I'd recommend drawing that step straight away to separate where metals and non-metals are. So the step starts from aluminium, which is a metal. So everything to the left-hand side of this is a metal, and everything to the right-hand side of this is a non-metal. That's really important when it comes to bonding and such. So as soon as you get into the exam, draw that step. Another thing I would also recommend writing on your periodic table is the charge of ions that are going to be on each. So remember, metals lose electrons, so they become positive ions. So everything in group 1 has 1 outer electron, it becomes 1 plus. Everything in group 2 has 2 outer electrons, they lose 2 electrons, so they become 2 plus. So I'll put that on that column. And group 7, everything in group 7 has 7 electrons, so it needs to gain 1 electron, so it becomes 1 minus. Everything in group 6 has 6 outer electrons, it needs 2 electrons to become fully stable, so they become 2 minus. So that's how your periodic table should look tomorrow. What I would probably also recommend putting on as well, remember as you go down group 1, the reactivity increases. So I can just say reactivity increases that way. And for group 7, the reactivity increases as you go up. So remember, it's the opposite for each of these. You have to know the names of each of these as well. So remember, group 1 are your alkali metals. You've got group 7, which are your halogens. And then you've got group 0, which are the noble gases. Remember, with the noble gases, they are inert, which means that they're not reactive. The reason why they're not reactive is because they've all got full outer shells. So that's the reason why it's group 0. So as an example, helium has 2 electrons, so it's got a full outer shell because it's the first shell. Neon's got 10 electrons, it's got 2 in the first one, and then 8 in the second, so it's got a full outer shell. So that's the reason why they're inert. They're not reactive, essentially. Okay, so moving on, we've also got the reactivity series as well, so you do need to memorize this. And there is a longer version of this, which I've seen online as well, but for AQA, you just need to know these. Now, an easy way to remember this, going down group 1 and group 2 as well, the reactivity increases. Looking at the reactivity series, you can see it goes potassium and sodium, which is, I'll just highlight on the periodic table. So potassium and sodium, you can see at first it's going down. Potassium being the most reactive, since it's below sodium, and then sodium. It then goes on to group 2. Lithium from group 1, and then it goes down to group 2, so calcium, and then magnesium. So it's the same rules for group 2. You've got carbon there as well. Now, the reason why you've got carbon is because you need to know about reduction with carbon, which we'll come on to. You've got carbon and hydrogen there as your non-metals, just to identify where everything is. You've got zinc and iron in between carbon and hydrogen, and then copper is not reactive. Okay, so we'll look at some past exam questions where they can ask the reactivity series. So it says here, figure 1 shows what happens when calcium, copper, magnesium, and zinc are added to hydrochloric acid. So we can see some bubbles of hydrogen are forming. It says, what's the order of decreasing reactivity for these 4 metals? So it says decreasing reactivity, meaning most reactive to the least reactive. You should know that copper is the least reactive. Looking at that reactivity series, you can see copper is right at the bottom. And then we've got calcium, magnesium, and zinc. So what I'd recommend, go back to your periodic table and try and figure it out from there if you do forget the reactivity series. So calcium, magnesium, and zinc. Well, calcium and magnesium's here. Since calcium's below magnesium, it's more reactive. So calcium is the most reactive. Then it's magnesium. We've also got zinc. We can see zinc is less reactive than both these two. And then it's copper. So it's calcium, magnesium, zinc, and then copper. So calcium, magnesium, zinc, and copper. So it's just this option. So yeah, what I'd say is don't just memorize it as is. It's worth comparing it to the periodic table, and you'll easily memorize it that way. Okay, moving just back up again. So important content. So just like biology, make sure you know what independent, dependent, and control variables are. Independent is what you're changing. Dependent is what you're measuring, and control variable you're keeping the same so it doesn't affect the experiment that you're doing. So looking at this question here, it says a student wants to make a fair comparison of the reactivity of metals with hydrochloric acid. So a fair comparison of the reactivity of metals is what they're trying to measure with hydrochloric acid. Name two variables that must be kept constant. Well, there's quite a few you could write, but just stick with just labeling two. Can you look for the amount of bubbles produced in the test tube? Yeah, in this case, if we were looking at dependent, you can count the number of bubbles that are probably being formed. Here, so it says name two variables that should be kept constant. Well, we want the hydrochloric acid to be the same concentration. So you could say concentration of hydrochloric acid, because the higher the concentration, the stronger the acid, and it's going to affect your results. You want to keep the concentration of hydrochloric acid the same. You could say the volume of hydrochloric acid as well. You don't want to be that to be a factor, so you want to keep the volume constant as well. You could say the temperature of the acid, and you could also say the mass of the metal as well. I'll just put some extras here. So a mass of metal or temperature of acid. Okay. Coming back up to here, so I've brought the state symbols here. So you've got solid, liquids, and gas, and aqueous. Remember, aqueous just means dissolved in solution, or even water, you could say. Reason why I wrote this is a lot of times in the exam, they say, what's the state symbol of so-and-so? And it might be like a worded question. Say, for example, it's a solid because in the question they've said white powder. If you actually write the word solid, you lose a mark because they've asked for state symbol. So just make sure you put the state symbol for whatever matter that is. So that's just to note that. So you have just reworded that there. Okay, you've got neutralization reactions, really common. So a neutralization reaction is where you get an acid and base, and that makes salt and water. So a lot of people get confused saying, well, how do I know what salt gets formed? So an easy way of doing that, let's just do it towards the bottom here. So an easy way to identify what the salt is in the neutralization reaction. In a neutralization reaction, acid plus base gives you salt and water. So do keep a few acids in mind. So you've got hydrochloric acid, you've got nitric acid, you've got sulfuric acid, and so on. So keep these in mind. And what you should notice with all these acids, they've all got H plus in. So let's say hydrochloric acid, for example, reacts with the base. Now bases have OH minus ions in, so I could say sodium hydroxide. Now let's say I had no idea what salt was going to be formed, but I do know water is going to be formed. Now what you need to remember with these reactions, water is always formed from the hydrogen in the acid and the OH minus in the base. So that gives you your water. So whatever's left behind, then that is your salt. So you've got chlorine there, you've got sodium. So it's just sodium chloride, this one. And then just always make sure that it's balanced as well. I'll give another example. Let's say, for example, we've got H2SO4, so sulfuric acid, and again, that's reacted with sodium hydroxide. The water comes from the hydrogen of the acid and the OH minus of the base, so that gives you your water. And then whatever's remaining, that gives you your salt. So you've got sodium sulfate. Now, how do you know what the actual molecule of sodium sulfate is? So this is where our charges come into place. So there's a few charges you do need to know about. So you should have access to this summary sheet. If you've not got this, do let me know. So these are the common ions that you need to know with their charges. So as you can see, sulfate is SO4 2-, just right here. And the reason why that's important So we've got sulfate, 2 minus. We know sodium is going to be +1. Reason why is because it's in group 1. So we just discussed right in the beginning, all group 1 metals become 1+. And this allows us to figure out what's going to be formed because we're just going to cross them. So I'll write sodium, write sulfate. The 1 drops to there, so it doesn't really affect it. And then the 2 just drops to here. So we get Na2 SO4. And then just make sure you balance, I guess. So that's the salt that forms from there. I'm not going to balance that for now, but do make sure you balance it as well. I would always recommend leaving balancing questions towards the end because it tends to take quite a bit of time if it is a really complicated one. So you'd rather get all the other marks in the exam and then just come back to balancing since it's only worth a mark or so. Okay, so just to be aware as well, if you asked how do you identify what is an acid and what's the base, acids have H+ ions, bases have OH-. Now, let's talk a little bit about hydrogen. We've just said that all metals become positive ions. So for example, we've got sodium has 1 outer electron, so it loses that electron and it becomes a positive ion. So all metals become positive ions. Just write that here. So metals become positive ions. And all non-metals become negative ions. But there's one exception to that. That exception is hydrogen. So hydrogen is the only non-metal that becomes positive. So this is the only one that becomes H+. Okay, what else could we say about hydrogen? They could ask, why is hydrogen floating in the middle of the periodic table? Well, hydrogen, how many electrons does it have? It's got 1 electron, so it's just a bottom number. So it's got 1 electron. So really, it should be in group 1 because remember, the group number tells you how many outer electrons it's got. So really, it should be in group 1. But because it's a non-metal, it should also be to the right-hand side of that step. So it's in a bit of a conflict, I guess. So that's the reason why it's just floating in the middle. Okay, so that's hydrogen. Moving on. Okay, universal indicator. So they always tend to ask how what could you use to show what's before or after a reaction. So if you've got an acid in the reaction before, I would just recommend saying the word red if you've got an acid in your equation, and if it turns into an alkali or a base, you could say purple. You could say bluish, but purple's just safe because it's a high pH. If they ask in terms of numbers, if you've got an acid, say a number between 0 and 2, so don't go any higher than that. The mark scheme only tends to accept an answer between 0 and 2. And likewise with alkalis and bases, just give a number between 13 and 14. So just give the ends of the spectrum. Something being neutral, I guess, just 7. Okay, so that's the universal indicator. Let's do another question. So we've got converting units here. So this question says a solution of hydrochloric acid contains 3.2 grams of hydrogen chloride in 50 centimeters cubed. So we've got a mass here, and we've also got a volume. It says calculate the concentration of hydrogen chloride in grams per decimeter cubed. So we've got that conflicting unit change. They've given us a volume in centimeters cubed. They want the concentration in decimeter cubed. Now, first of all, you need to know what the equation for concentration is. And you can, if you do forget in the exam, you can figure out a lot of equations from. So you can see that the units here says grams per decimeter cubed. Grams per decimeter cubed is just like this, which is the same as grams over decimeter cubed. So that per means divide. So really, you're just doing mass divided by volume. So if you ever forget, you can just figure it out from the units. Mass divided by volume. It's also quite common as well for them to ask what should the units be, and you figure out the units like that as well. So what you're doing with the equation and substitute your units in. Okay, so our mass is 3.2 grams. However, our volume is in centimeters cubed, and we need to change the centimeters cubed to decimeters cubed. So I would also recommend drawing this somewhere as well when you get into your exam. So converting units between centimeters cubed, decimeters cubed, and meters cubed. So you can see it's all in alphabetical order, so C, D, M. And to go this way, we are dividing by 1,000. And if you want to go meters to decimeters cubed or decimeters cubed to centimeters cubed, you're timesing by 1,000 each time. So yeah, the way you can remember it is it's in alphabetical order and you can just divide it. So let's just keep that over here. Okay, so we're changing the 50 centimeters cubed to decimeters cubed. So we're dividing by 1,000. So we're doing 50 divided by 1,000 underneath. Putting that in the calculator, we get 3.2 over 0.05, and that gives you 64 grams per decimeter cubed. So that's a calculation one. Let's have a look at another calculation. So it says here, calculate the percentage by mass of oxygen in ammonium nitrate. So it's saying how much oxygen is in this full ammonium nitrate. We can see there's 3 oxygens here. So there's just 3 oxygens. They've been kind to actually give you what the AR is and the relative formula mass. If they didn't give you this, you have to figure it out from the periodic table. Remember, it's just the mass numbers you're taking on top. So it says here oxygen 16. If you go to the periodic table, you can see oxygen is 16. So just in case they don't give you them, you should be able to figure them out from the periodic table. So we're working out oxygen, which is 16 times 3. We're dividing that by the total relative formula mass, which again, they've been kind enough to give, which is just 80. And since it's a percentage, we always times by 100. Putting that in the calculator, we get 60%. That's relatively easy 3 marks for that. I probably would be more explicit that this is like for the 3 times of oxygen, for example, on the top, and then that's the MR. So just tell the examiner explicitly that you understand where the numbers are coming from. Okay, let's just go back up to here and make sure we've not missed anything. The early periodic table was arranged in order of atomic weight. So it's quite a common question, this. How was the early periodic table arranged prior to what it looks like today? It was in order of atomic weight. And then Mendeleev came along. He left gaps in the periodic table to allow for undiscovered elements to basically be slotted into there. Okay, another thing I would recommend going over as well for tomorrow's exam is the history of the atom and how it is the nuclear model it is today. I'm not going to go over all of it in a lot of detail, but it is on the summary sheet, so it's right here. Make sure for each like history thing that happens, you know the scientists that said it and what they said. So for example, Thomson proposed the plum pudding model, where there were he thought it was a ball of positive charge with negative electrons just on it, like a plum pudding. Then Rutherford came along and he did the alpha particle skyring experiment. And then Bohr came along. He then said that electrons are at shells away from each other. And then Chadwick finally came along and said about the neutrons. So neutrons are the last thing to be discovered. So definitely do go over the history of the atom. Make sure you're aware of all the relative charges and the relative mass. They might ask you a question of, well, why is so? Let me see if I can write on this. Okay. So you can see here, sodium, it's got a mass number of 23 and a proton number of 11. The proton number, which is the bottom number, and the electron number is the same. They might ask you, why are they the same? Well, the reason why they're the same is because all atoms on the periodic table do not have a charge. They're not an ion. So therefore, the number, it just needs to be neutral overall. The protons are positive. So if I've got 11 plus, because of the protons, I need 11 minus as well to cancel that out. The electrons are negative. So that's the reason why we've got the same amount of electrons, same amount of protons. And then remember, neutrons is just the mass number. Take away the atomic number, so the proton number, because the mass is only including the protons and the neutrons. It doesn't include the electrons. Again, if they ask you, why does it not include the electrons? It's because the electrons are very small. They barely weigh anything. Don't say in the exam that they weigh 0. You could say 0.0005, you could say 1 over 2,000, you could say 1 over 1,860, but just don't say 0 because nothing can have a 0 mass. So yeah, the reason why electrons are not in the mass number is because they barely weigh anything, so it's negligible to count A in the overall. Make sure you know what isotopes is. So isotopes are atoms of the same element, but they just have different neutrons. So the mass number will be different, but the proton number stays the same. If you're ever asked to identify something in the exam, so it's, say for example, X, and it's got 7 and, I don't know, 15 on top, and you're asked to identify what is this atom, you always look at the proton number as an identifier. You never look at the top mass number. So on the periodic table, I would check, okay, what's got 7 on the proton number, and you can see here it is nitrogen. So you would say this is an isotope of nitrogen, so nitrogen 15. So that would just be nitrogen 15.7. So yeah, remember the proton number is the identifier, not the mass number. Okay, let's go back to here. Okay, we've got some reaction profiles. So what's an exothermic and an endothermic reaction? An exothermic reaction is one which gives out heat, if you're thinking of it in basic terms. So it's the more common reaction. So something like combustion, which you learn for paper 2, is an exothermic reaction. Respiration is exothermic. That's the reason why we get hot when we're respiring. And endothermic reactions take in heat. So for example, photosynthesis is an endothermic reaction. It's taking in light, in turn heat. So therefore it's an endothermic reaction. These are more or less common. You need to understand the reaction profile. So just explaining this to you briefly. For the exothermic reaction, you always draw your reactants higher than your products. Reason why in an exothermic reaction, you're losing heat energy. That's the reason why your products are lower than your reactants. In an endothermic reaction, you're absorbing heat, you're taking in heat. So the heat of the products has increased, the heat energy, so therefore it's increased. Okay, so what's this little hump that's here? This little hump that's here is the activation energy. Remember, the activation energy is just from the reactants. So you can see just from the reactants to the top of the peak. Again, from here, from the reactants to the top of the peak. You can see it requires a lot more energy to start off an endothermic reaction because you're putting heat into that reaction. The activation energy is the minimum amount of energy to start off that reaction. Now, if you think about collision theory, you want to hit these particles with enough force that they begin to react, and that's what the activation energy allows for. It allows for that reaction to take place. You can lower the activation energy by using a catalyst. Now, if you use a catalyst, that lowers the activation energy. If they ask, how does it lower the activation energy? You say the catalyst, it speeds up a reaction without getting used up, but it also provides an alternative pathway for the reaction. A lot of people tend to lose this mark. So saying that it provides an alternative pathway, so you can see it's this lower peak, which requires much less energy. Okay, so that's reaction profiles. It could get you to draw them in the exam. They could get you to label them in the exam. But that's the reaction profiles. Okay, let's talk a little bit about bonding. They could give you any molecule or compound in the exam, and they could ask you to identify what bonding is this. All you have to do is check, is it metal or non-metal? To identify if it's metal or non-metal, look at the periodic table. You've got your little step here. If it's to the left of that step, it's a metal. If it's to the right of that step, it's a non-metal. So for example, if I had sodium chloride, sodium is here, chlorine is in group 7, so it's a metal and non-metal, so it's ionic bonding. If I had something like carbon dioxide, well, carbon is a non-metal, oxygen is also a non-metal, so therefore it's covalent bonding. So don't be worried about like what you get given, just check which side of that step it's on. Ionic is metal and non-metal, covalent is non-metal, non-metal, and metallic is metal and metal. They all differ in terms of electrons. So ionic bonding is a transfer of electrons. One will give it, which is the metals, and one will gain it, which is the non-metals. Giving you a quick example over here. Right there, we've got lithium chloride. So the lithium has given its 1 electron to chlorine, so it's become positively charged. It's +1 because it's lost only 1 electron. So if it lost 2, then it would have been 2+. Chlorine has gained that, so it's become 1- since it's gained just 1 electron. So the charge just means how many electrons is actually gained or lost. Okay, let's go over to covalent bonding. So we've got an example question here. It says draw the electrons in the outer energy levels in figure 3, so we can see it's O2. So oxygen has 6 outer electrons because it's in group 6. So 1, 2, 3, 4, 5, 6. So for this oxygen atom to be stable, it needs 2 more electrons. So each of these oxygens need 2 more electrons. When you're drawing covalent bonding, I'd always recommend doing your overlap first. So I'm going to use X's to represent the left-hand side of the oxygen, and I'm going to use dots to represent the right-hand side. So this oxygen has 6, but it needs 2 more. So it's going to get 2 from the right-hand side. Likewise, the right-hand side has 6 and it needs 2 more, so it's going to share 2 from the left. Let's just draw in all the remaining crosses and dots. We've drawn 2 crosses, so we've got 1, 2, 3, 4 left. So remember 6 crosses altogether. And the dots, we've got 2 dots in the middle. We need 6 altogether. So 1, 2, 3, 4. And you can see each have 8. So 1, 2, 3, 4, 5, 6, 7, 8. And likewise for the right-hand side. So yeah, if you get, I would say covalent bonding is probably one of the more trickier ones to draw. Always do the middle first and then the outer. Okay, so sharing electrons there. In terms of ionic bonding, covalent bonding, and metallic bonding, if you're ever asked questions like, why in covalent bonding do they have low boiling point? You're talking about weak intermolecular forces. Intermolecular forces. If you ever asked for ionic bonding or metallic bonding, what's the reason they've got high melting and boiling points? What makes them strong? And so on. You're talking about strong electrostatic forces for both of these. So strong electrostatic forces. So if in a question you're able to identify what kind of bonding is going on, then you know the reasons why certain things are happening. What you need to also be careful of as well is where the electrostatic forces are between. So remember, electrostatic forces are between something positive and something negative because they're attracting together. Think a bit of physics, like magnets attracting to each other. Here in ionic bonding, the strong electrostatic forces are between the positive metal ions and the negative non-metal ions. So that's where your strong electrostatic forces are between. That's what allows the lattice structure to come about as well, because you've got positive, negative, and it starts forming like a cube shape. In metallic bonding, you don't have negative ions. We don't have non-ions. We've just got delocalized electrons. So you can see here all these minus signs, and then you've got positive ions in the middle. You've got a sea of delocalized electrons. The electrostatic forces are between the positive metal ions and the negative electrons. So even though both ionic and metallic bonding have the same reasoning, like strong electrostatic forces, the electrostatic forces are between different things. So here you would say between positive metal ions and the negative electrons. I would even say negative delocalized electrons. Try and not say the word free in the exam. The mark scheme does want the word delocalized electrons. It just means free electrons which are on that metal. That's the reason why metals can conduct electricity and thermal energy. Ionic bonded stuff can only conduct electricity if they're molten. And that leads nicely to electrolysis as well. So for electrolysis, you need to know the example of an aqueous solution. You need to know of an ionic lattice and the reason why they extract metals. So we'll come on to that, but just keep that in mind. For ionic compounds to conduct electricity, they have to be made molten. I think I do have a question on that actually. It says here, why does solid sodium chloride not conduct electricity? Okay, in this question, you should be thinking, okay, well, what is sodium chloride? Sodium's in group 1, which is a metal. Chlorine's in group 7, which is a non-metal. So metal and non-metal, this is ionic bonding. So therefore, this is an ionic compound. And the reason why a solid ionic compound does not conduct electricity is because ions are in a fixed position. So all you would say is the ions are not free to move. Now, let's say it was a 2-mark question, for example, you had to put 2 points down. Like they said, well, how do you allow it to conduct electricity? For it to conduct electricity, you need it to be molten. So you can allow the ions to move. And that's what leads to this here. Okay, so what I would say, especially with chemistry, try and link there's 5 sections. Make sure you link everything together. It's easier to remember. Okay, I've got a 6-mark question here, and I've shown the mark scheme of what they actually expect in these questions, because bonding tends to come up almost every single year. It says here chlorine reacts with sodium and with hydrogen. So 2 different examples. Chlorine is reacting with sodium, so therefore sodium chloride, which is the ionic one. And chlorine reacts with hydrogen, so chlorine and hydrogen are both non-metals, so therefore this is covalent. And it's saying compare the structure and bonding in sodium chloride and hydrogen chloride. So for 6 marks, what you're essentially describing is this table here between ionic bonding and covalent bonding, which is quite a good 6-marker. So you can describe how the electrons are getting transferred. Looking at the mark scheme here, you can see they've said which bonding's happening, why you know it's that bonding. So like metal and non-metal, 2 non-metals. What happens with the electrons? You can talk about the structures as well. So sodium chloride is a lattice structure. You can talk about electrostatic forces with this. The covalent one, you've got the intermolecular forces that you can speak about, and so on. Okay, one common misconception is even though covalent simple molecules, so stuff like oxygen, stuff like hydrogen, and so on, they are considered weak, but they do have strong covalent bonds, even though they've got weak intermolecular forces. So I just want to explain this concept here. Have I got space for it? Yes, I do. Okay, so what are intermolecular forces? Now let's imagine you've got a glass of water, and in that glass of water, you're going to have loads of H2O particles. You're not just going to have 1 or 2, you're going to have loads in a bottle of water, so they're all H2O. Now, them H2O molecules all need to be joined together by something, and what joins them together are intermolecular forces. So let's draw that out in a different way just to show you what intermolecular forces are. Let's say we've got loads of H2O, like so. Just draw a few here. Okay. So you've got, these are all representing each little circle. So how are all these joined together? They're joined together by intermolecular forces, the hydrogen with the oxygen, just like so. So these here are the intermolecular forces which are weak. However, the actual covalent bond is strong. So make sure you understand that comparison between intermolecular forces, but the covalent bonds being strong. That's the reason why we've got giant covalent structures like diamond, like graphite, like silicon dioxide. They're all strong because they've just got the strong covalent bonds that are repeating. So like in diamond, you've got carbon bonded to 4 of the carbons, which is bonded to 4 of the carbons, which makes diamond really hard. So that's diamond. With diamond in particular, make sure you say the word hard. They don't accept the word strong in the mark scheme, unfortunately. So yeah, just wanted to differentiate the difference between a strong covalent bond and a weak intermolecular force. So if you think about it, when you're boiling water, for example, would diamond have strong intermolecular forces? You wouldn't talk about intermolecular forces in diamond. You just talk about the strong covalent bonds. It's a bit of a oxymoron saying strong intermolecular forces, because intermolecular forces are weak. So you wouldn't speak about that in diamond sense. You just talk about the strong covalent bonds in diamond. So don't say strong intermolecular force. Talk only about intermolecular forces with simple molecules. So stuff like hydrogen, water, oxygen, and so on. Okay, so this question here, we can see we've got some simple molecules here. And they're all non-metal, so therefore it's all covalent bonding. It's showing the boiling point. It says explain why the boiling points in table 2 are low. So what you're saying is that they've got weak intermolecular forces, because it's that's your first mark. So you say weak intermolecular forces between, and your second mark comes from that it needs little energy to overcome these forces. So that's your second mark. Just don't waffle or anything like that, or talking about the covalent bonds or anything. Just stick to your 2 marks that you need to write down. One other thing I wanted to mention with this as well. So say, for example, this is liquid water, and I'm changing it to a gaseous state, so steam. The steam is still H2O. So if I go from liquid H2O to steam, it's still gas, but it's still H2O. So there's no chemical change. It's just a physical change. It's a liquid gone to a gas, but it's still H2O. It's just the intermolecular forces you've overcome. What does intermolecular forces mean? It's just these little blue things here, and they only happen in covalent substances, not ionic and not metallic. Okay, so one thing I also wanted to point out here as well, so fluorine, chlorine, bromine, that's the order it's in. Looking at the periodic table, fluorine, chlorine, bromine, they could potentially ask you as well, as you go down, why is the, where's it gone? Yeah, so why is the boiling point increasing as you go down? So you can see the boiling point is increasing. So if you had a 2-3 mark question on that, why is the boiling point increasing? You say the molecules get larger as you go down the group because there's more shells. So the molecules are getting larger as you go down the group. If the molecules are getting larger, then you've got more intermolecular forces that you need to overcome. So therefore, boiling point is going to increase as you go down, because more energy is needed to separate the molecules. So that's a classic 3-mark question as well. They could ask you that. So it's all about increasing size of molecules, so increasing size of molecules. But just be careful not to talk about intermolecular forces with ionic or metallic bonding, just covalent bonding, and that's it. Okay, so here I've got an example of group 1. So explain why sodium is less reactive than potassium. Looking at the periodic table, where is sodium and where is potassium? Sodium is above potassium, and we've said as you go down, it gets more reactive. What's the reason it gets more reactive? If you think about it, group 1 metals are losing electrons. They want to lose that one outer electron. So what's the difference as you're going down the group? Well, as you're going down the group, the element's getting bigger, it's getting more shells. So that outer electron is further away from the positive nucleus. So if it's further away, it's easier to lose. So because it's easier to lose, the reactivity increases. So let's put that into words for this question here. Explain why sodium is less reactive than potassium. So let's talk about it in the sense of sodium. So we could say sodium has fewer shells than potassium. Okay, 1 mark. So therefore, why is that relevant? You say the outer electron is closer to the nucleus because we're talking about sodium. So sodium has fewer shells, so therefore the outer electron's closer to the nucleus. So therefore there's a greater attraction between nucleus and outer electron. You could say the nucleus is positively charged because it's only the protons that make it positively charged. Great attraction between nucleus and outer electron. And then your final mark is, well, what's the relevance of that? You just say the outer electron is less easily lost. And I would recommend writing like this in the exam because you're explicitly saying to the examiner, here's my 4 points with no waffle. So that's a classic way you can write about group 1 going down. Now, if they do end up asking you about group 2, it's exactly the same reasons. As you go down group 2, the reactivity also increases as well for the same reason as well. And then in terms of group 7, the halogens we've already spoken about. As you go down, molecules are getting bigger, so the electrons moving away from the positive nucleus, but it's the opposite. Remember, in non-metals, they want to gain an electron, and it's harder to gain an electron as you go down because the molecules are getting bigger. That's what you say on the flip side. Okay, moving on. Let's talk a little bit about electrolysis, one that everyone tends to hate. So what you need to remember about electrolysis is it's just electricity used to split a substance. And the reason why we speak about it in Chemistry Paper 1 is because, let's go back to this reactivity series here. Now, when we're extracting metals, we can do 2 processes for extracting metals. Let's put this here. Now, for extracting metals, we could either do reduction by carbon. But if we cannot do a reduction by carbon, we're then going to be using electrolysis. So where can we not use reduction by carbon? We can only use reduction by carbon on anything less reactive than carbon. So remember how I said there's a reason why carbon and hydrogen's here. It's because everything below carbon, so zinc, iron, and copper, we can extract this using reduction by carbon. So let's speak about how we would do that. Okay, extraction. Okay, there you go, extraction of metals. So if we're using reduction by carbon, what does reduction mean? So if you're doing just foundation, you only need to know reduction and oxidation in terms of just oxygen. But if you're doing higher, you need to know in terms of electrons and oxygen. So let's do a little table. Let's do a little table on this sheet, actually. I'm going to get this sent out to you after. So reduction and oxidation. In terms of oxygen and also in terms of electrons, but remember electrons is just for higher tier. Okay, so oxidation is a bit self-explanatory with, if I'm doing foundation, do I need to know moles? No, you don't need to know moles. You don't need to know moles if you're doing foundation. Okay, so oxygen, in terms of oxidation, bit self-explanatory. In oxidation, you are gaining oxygen. So therefore, in reduction, you're losing it. And then for electrons, it's opposite. So for higher tier students, just remember oil rig, where oxidation is loss and reduction is gain. So you can see it's just the opposite way around. Oops. So that's gain and loss. So yeah, so a lot of people confuse this mnemonic for the oxygen part. So just remember oil rig is just for electrons, so just for higher tier. Okay, so we've just said, let's go back to the oxygen example. Now, a lot of people, when they're trying to figure out what's getting reduced and what's getting oxidized, try and look at the electrons, but try and look at the electrons, the oxygen. It's a lot easier to figure out what's going on. Let's go back to that example of reduction by carbon. So remember, metals are found in ores. Ore is just a rock that has a sufficient amount of metal to make it worth your while to extract that metal from that ore. Okay. Metals less reactive than carbon, as we've just said, zinc, iron, and copper can be extracted with reduction by carbon. Anything that's more reactive than carbon, we have to remove that using electrolysis. Okay, so here's an example. We've got iron oxide plus carbon gives you the iron. So we can see here, let's write this down. So just so we can understand what's getting. Okay, so we've got iron oxide is going to iron, first of all. So you could say the iron oxide, since it's losing oxygen, it's getting reduced. And the carbon, so plus carbon, we'll leave the balancing for now. That changes the carbon dioxide. So because the carbon's gaining oxygen, it's getting oxidized. So first step is try and just see what's happening with the oxygens. It's easy to figure out what's getting reduced and what's getting oxidized if they do ask you what's getting reduced and what's getting oxidized. And the whole purpose of extractions of metals using reduction by carbon, we want to get the metal out. So you can see we've got the metal out there. So they could ask you this in terms of iron, they could ask you in terms of zinc or copper. That's reduction by carbon. If we are using electrolysis, we'll come on to electrolysis actually. One other thing I want to mention as well, final thing with the reactivity series, they could ask you about displacement reactions. Let's go with displacement reactions. So displacement reactions is kind of in the name. The more reactive thing will displace, so get out, the less reactive thing. So if I was using, let's use the halogens, for example. So as you go down the group, the reactivity is decreasing, remember? So the reactivity increase is going up. So that means fluorine's more reactive than chlorine. So let's do an example using that. If I had potassium chloride, and the reason why I know it's that is because potassium is, what is potassium in? Potassium's in group 1, so it's just got 1 plus charge. Chlorine's group 7, so potassium chloride plus fluorine. Remember, fluorine's diatomic. Fluorine, oxygen, hydrogen, they're all diatomic molecules. So because fluorine is more reactive than chlorine, the fluorine's going to displace the chlorine out. So therefore it becomes KF, and then you form chlorine as a byproduct. Just balancing that out. Yeah, that's okay. So that's displacement reactions in terms of reactivity using the periodic table. You need to know displacement reactions as well in terms of this reactivity series as well. So if something contained sodium in, but then it was reacted with something with potassium, because potassium is more reactive than sodium, the potassium is going to displace the sodium. So that's how displacement reactions work in terms of reactivity. Now remember, the more reactive something is with in terms of a metal, it's how readily available it can lose that outer electron. Okay, let's see what questions we've got on here. Okay, so we've got, let's talk about this electrolysis here. So when electricity is used to split a substance, so we've spoken about using reduction by carbon to extract a metal. Let's talk about electrolysis to extract the metals. This is from the summary sheet. So metals can be extracted from molten compounds using electrolysis. So we've just spoken about why it has to be molten. It's molten because we need the ions to be free to move. Remember, ionic lattices do not conduct electricity unless you make them molten. That's the reason why we turn it molten. Electrolysis is then used to extract the metals that are too reactive to be reduced to carbon. So therefore we use electrolysis for the ones higher up. Otherwise we would just use reduction by carbon because it's a lot cheaper than using electrolysis. Aluminium is manufactured by the electrolysis of a molten mixture of aluminium oxide and cryolite. This is something you need to memorize, these two. So aluminium oxide and cryolite, that's what's mixed for this one. Cryolite's used to lower the melting point of aluminium oxide. So it's just making the reaction cheaper to actually do. That's the reason why we use cryolite. We're using carbon at the anode. So the anode needs to be replaced regularly as it reacts with oxygen to produce carbon dioxide, which you kind of can see with reduction with carbon as well. That carbon dioxide gets formed. Remember, carbon dioxide is a gas, and that's going to escape away. If these electrodes are constantly reacting with the oxygen, and forming carbon dioxide, they're going to get smaller and smaller, so you need to keep replacing that. If they ask, what could you, I think I've got it here actually, suggest an element that could be used to make inner electrodes, you could say graphite, but you could, because graphite is carbon, or you could just say carbon as well. It doesn't, you could get a mark for either or. So yeah, the electrodes are made of carbon. We'll come back to this. There's one important aspect I want to explain of electrolysis that everyone gets confused by. So electrolysis, few different words that you need to know. So you've got cations and you've got anions. Now, if you like cats, you can think of cations as the positive one. So these are the positive ions, and we know that positive ions are metal ones, metal ions. So if cations are positive ions and anions are negative ions, so it's just the opposite. So cations and anions are just describing. Could you say diamond as it's also carbon? No, you can't say diamond just because, first of all, it's way too expensive to use, so you wouldn't use it. It's graphite that mainly gets used. So either say, for that question that we just did, either say graphite or carbon, one of the other. Okay, so cations and anions. Now, positive attracts to negative. So the cations, they bond, they will get attracted to the cathode. And the cathode can't be positive because positive can't attract to positive, they repel. So the cathode must be negatively charged to be able to attract the cations. Likewise with the anions, because the anions are negative ions, they're going to get attracted to the anode because they're anions. And the anode has to be positive since it's attracting negative ions. An easy mnemonic to remember these, you could remember panic, which means positive anode, negative is cathode. Not too sure if anyone's heard that mnemonic, but this is referring to the electrodes, if you do ever get confused. And then you can just think of cats, so therefore cats are positive, if you like cats. Okay, now another concept. If the metal ions, so let's say in this example here that we had up here, the aluminium 3 plus is becoming aluminium, which we can see here. It's becoming aluminium. So the ion, which has lost 3 electrons, is becoming an aluminium atom. So the 3 electrons that it's lost is gaining them back. So a lot of people get confused by this concept because you always think metal ions, they've lost electrons. They have. Going from an atom to an ion, you lose electrons, but we're going from the ion back to the atom, so it's gaining them electrons back. So that's the reason why we've got the plus 3 electrons. Okay, so that's basically what's happening. You split the overall reaction into 2 reduction or oxidation reactions. Now these half equations, only higher tier need to know this. If you're doing foundation, you don't need to know how to make them. You should just know what's happening in terms of oxygen. Okay, let's move on. So that's one example of electrolysis you need to know. Another version of electrolysis you need to know is what happens using solution. So it's similar. You've got a solution of something which will have cations and anions. So the sodium will be your cations because it'll be positive sodium ions, and then your chloride will be the chloride ions. So they're your anions. And then they react with the electrodes. Let's just roughly talk about the aqueous version of that. So, okay, so we've just spoken about using electrolysis to extract metals, where they give you the aluminium oxide in the cryolite example. You need to know about electrolysis of aqueous solutions, which I'll just talk about now. But you also need to know generically as well about electrolysis of molten ionic compounds, the fact that you have to make a molten. Okay, let's talk about the aqueous solution ones. So when an aqueous solution is electrolyzed, the ions in the water must be considered, meaning you've got sodium chloride, but you've also got your water that is in is going to form H plus, and and OH minus, which we can see here. There's a H plus and the OH minus has come from the water. So you need to consider that as well with the aqueous solutions. Hydrogen ions and hydroxide ions come from the water, which we've just said. At the negative electrode, which is cathode, the hydrogen gas is produced if the metal is more reactive than hydrogen. So that's the reason why we've got the hydrogen in the reactivity series as well. So you can see only copper is less reactive than hydrogen. Everything else is more reactive than hydrogen. So going back to here, hydrogen gas is produced if the metal is more reactive than hydrogen. So if it's something that's not copper, most likely hydrogen is going to be formed. The half equation, only higher students need to know about that. In terms of half equations, your atoms need to be balanced and your charges need to be balanced. So for example, I've got 2 minus on the left-hand side because I've got 2 electrons. And there I've got 2 OH minus on the right-hand side, which gives it 2 minus overall on the right-hand side. So just keep that in mind. Charges also have to be balanced as well as actual atoms itself. And then at the positive electrode, which is an anode, oxygen is usually produced. This is a rare case scenario. So however, if the halide ions, so like chloride, are present, a halogen like a halogen will be made. So for example, the chlorine changes to chlorine. If you've got fluoride ion in there, that changes to fluorine, and so on for all the other halogens as well. And that's really all you need to know about electrolysis. We've just spoken about this one here. If they ask the reason why electrodes should be inert is so they don't actually react with the electrolyte. Electrolyte being the solution, we want them to be inert, so they're just there. They're not affecting the actual reaction that's happening. But the whole point of electrolysis is just splitting using electricity in the most basic form is what that is. So when electricity is used to split a substance, that's the main idea of it. Okay, just before doing this, I'm trying to think if there's anything else that's really important to mention, because there's still quite a lot to chemistry as well. So I've gone over the main, but what I'm going to do now is I'm going to cover all the higher stuff, so just some higher calculations. If foundation do want to stay on, you can stay on if you do not ask questions at the end, but just for the next 10 minutes or so, I'm just going to do some higher questions. So let's just do these ones. So copper and chlorine are produced when molten copper chloride is electrolyzed. Complete the half equations for the reactions at each electrode. So we've got the half equation at the negative electrode and half equation at the positive electrode. How does displacement work in the reactivity series? So displacement is where the more reactive thing will displace the less reactive thing. So it just swaps it over. That's all displacement is. So that's how it relates to the reactivity series, just like it does with the halogens, for example. What question would they ask for electrolysis? They could ask you the process. They could ask you to identify the cation, the anion. They could ask you what's getting oxidized, what's getting reduced, and so on. So just on that summary sheet, I'll keep this on screen if you just want to get a screenshot. That's literally all you need to know for electrolysis. Electrolysis of aqueous solutions and electrolysis of the ionic molten one. So it's 2 examples, really, to be fair, that you need to know. Okay, going back to this, so it's still on electrolysis. You want to always balance out your charges on each side, and you need the same atoms on each side as well. So remember, conservation of mass. Whatever you put in, you have to get out as well at the end. So starting off with this one, we know the copper 2+ is just going to change to copper. So it's quite nice that they've just given just a little line over there. However, we've got a 0. Our coppers are balanced, by the way. We've got 1 copper here and we've got 1 copper there, so that's fine. It's just the charges are not balanced. We've got 2+ here, but we've got 0 here. So we need the left-hand side to become 0, and the only way we can make that a 0 is if we add 2 electrons, because 2 minus plus 2 gives you 0, so 2+, and well, I'll write 2 and then minus 2, because it is minus 2 equals 0. So the left-hand side 0, the right-hand side is 0. So don't think of it too complicated in what's gaining electrons, what's losing electrons. Just balance it is the main thing. We can never minus electrons, by the way. You cannot do this. I'll put a big red on that. So don't ever write minus electrons. Okay, with this one, the chlorine, well, it's going to become a diatomic chlorine, just like that. They're giving you a bit of a clue. They've got a longer line there, so they probably want you to write a bit more things. We've got our chlorines are balanced, so we've got 2 chlorines here, 2Cl, and we've got 2 chlorine atoms there, so they're balanced. Our charges are not. We've got -2 here because 2 times -1 is -2. But on the right-hand side, we've got 0. So let's change the right-hand side to be -2 because we can't -2 electrons. We're not allowed to do that. So if I add 2 electrons here, now I am -2 on both sides. So that's how you actually do your half equations. It's better to think of them in just a balancing sense. Okay, let's do some calculation questions. Now, moles, there's 3 ways you need to think about moles for higher students. For moles, you can either do, where should I write it? I'll just write it here. So 3 ways to think of moles. Moles could equal mass divided by mR, which you need to remember. Your moles could be Avogadro's number, so the 6.023 times 10 to the power 23 particles in 1 mole. So what Avogadro is saying is in 1 mole, you've got 6.023 times 10 to the 23 particles in just 1 mole. And finally, you can think about moles as molar ratios. So you know your numbers that's in front of an equation. So say for example, have I got one here? I don't. Let me just quickly do an example. Say for example, I had hydrogen plus oxygen gives water. I have to stick a 2 there, 2 there. Yeah. Okay, so for example, I've got 2 moles reacting with 1 mole because there's a 1 there. That gives me 2 moles here. So there are your 3 ways that you're thinking of moles. So molar ratio, your moles in terms of Avogadro's number, and you've got moles equals mass divided by mR. Let's look at this question here. How many atoms are there in 1 gram of argon? And it's told you Avogadro's constant. And it's giving you the relative atomic mass of argon as well. So all you're doing is, because we've got 1 gram, what is moles? Moles equals mass divided by mR. So let's work out the moles of argon, which is mass over mR. So mass is 1 gram over mR. mR and AR are really the same thing. AR is just of 1 like atom, 1 element, and mR is like if it was carbon dioxide, so multiple, but really they're the same thing. It's just mass number. So divided by 40. So that's the moles. I'm just gonna leave that. Or I could just write, yeah, that's 0.025. So to work out the number of atoms in 1 gram, I'm going to do the moles, which is 0.025. And I'm going to times that by Avogadro's number, 6.02 times 10 to the 23, because that's how many particles, so atoms will be in there. And what that gives me is 1.505 times 10 to the 22 amount of atoms in 1 gram. They would have accepted the mark if you rounded it to 2 decimal places as well. So if you said 1.51, they still would have given you the mark as well. Okay, finally, let's do the 6-mark question. And then if anyone's got any questions about chemistry, we'll just open the floor to the chat. So let's have a look at this one. So 0.2 grams of magnesium is added to 100 centimeters cubed of hydrochloric acid. So I like labeling what they're given. So they've given us a mass of magnesium, and they've given us a volume of hydrochloric acid. It says the hydrochloric acid is added in excess, so they keep adding the hydrochloric acid until the magnesium is fully reacted. That's basically what that means. It says calculate the concentration of magnesium chloride solution in grams per decimeter cubed. So concentration is just mass divided by volume, which we can see explicitly in the units anyway, is grams per decimeter cubed, so mass divided by volume. And they've given us a relative atomic mass. 6 marks. So what I probably would start with is actually finding out the moles of magnesium. So moles of magnesium, we've got, which is mass divided by mR, so 0.72. What's the mR of magnesium? It's just 24. That gives me 0.03 moles. Got the moles of magnesium. I've totally cut out the equation. They did give us an equation, but I've just cut it out from above. But it was magnesium plus a hydrochloric acid gives magnesium chloride, and I think it was hydrogen. So that becomes a 2 there. Okay, pretty sure that was the equation given. So now we're going to look at the molar ratios. We've got magnesium reacting with 2 moles of hydrochloric acid, and it's formed 1 mole of magnesium chloride. We want the concentration of magnesium chloride, so I care about the moles of magnesium chloride. Just tell the examiner it's a 1-to-1 ratio, ratio between magnesium and magnesium chloride. So therefore, the moles of magnesium chloride is also 0.03. So you have to give a reason for that assumption. So the reason is because we've got a 1-to-1 mole. They did give you this equation, by the way. I just chopped off the question. Okay, so we've got the moles of magnesium chloride. That's good. But to work out concentration, I need mass and volume. I've got the volume, 100 centimeters cubed, which I do need to convert to decimeters cubed. We'll deal with that after. But we need to work out the mass. Now, if moles equals mass divided by mR, then mass equals moles times mR. So we've got, mass of magnesium chloride is going to be the moles, which is 0.03, times the mR of magnesium chloride, which is 95. That gives us 2.85 grams. So we can work out the concentration now. Concentration equals mass, which is 2.85, divided by the volume, but the volume's in the wrong units. It's in centimeters cubed. We need it in decimeters cubed. I'll just do that up here. So 100 centimeters cubed, we're going to divide that by 1,000 to get decimeters cubed. So we get 0.1 decimeter cubed. We're dividing that by 0.1, and what we get is 28.5 grams per decimeter cubed. And that was for 6 marks. So what I would recommend, moles equals mass divided by mR, and molar ratios is the most important thing for these questions to get started, and it will flow from there. So that's the end of that. There is still quite a lot of chemistry content that I could keep going on forever, to be fair. But it is all on the summary sheet. If anyone's got any questions, do ask them now, and I can explain them on this session now. Can you explain polymers and allotropes of carbon? Yeah, sure. So polymers is basically just plastic. Let me have a quick look. Let's go over here. I'll get all these notes sent out after as well. So allotropes of carbon just basically mean how carbon's bonded differently to give rise to different substances. So what you've just described there are all giant covalent structures, where the allotropes of carbon, you've got diamond. Each carbon, in diamond is bonded to 4 other carbons. So we don't have any free delocalized electrons to conduct electricity, which makes it good for jewelry. And it's also really hard as well, because it's that carbon repeated with carbon. Another allotrope of carbon is graphite. Now in graphite, each carbon is bonded to 3 other carbons, meaning there's 1 delocalized electron. And that delocalized electron allows it to conduct electricity. So graphite's what's in pencils. So the reason why if you stick it in a plug, you'll get an electric shock because it's got that 1 delocalized electron. And you should remember that it's got a hexagonal shape just like this, and it's got loads of layers of that. So this repeats this hexagonal layers. Another one is graphene. Now graphene is just 1 layer pulled out. And the reason why graphene is pretty good, since graphite conducts electricity, so does graphene, and it's just 1 atom thick, so we can use it for electric boards and such. Another giant covalent structure is silicon dioxide. Sometimes they call it silica, not spelled like that. We've also got the polymers, which are plastics. That's just repeating chains of carbons, which you learn more about in paper 2, to be fair. How will a question look like asked based on this? They'll say, why are giant covalent structures strong? You can say because they've got strong covalent bonds, a lot of energy to overcome the covalent bonds. You can say, they could ask about, give other examples of giant covalent structures as well. And they could just ask to describe each of the structures. So you could say diamond is carbon bonded for the carbons, which allows it to be hard, and so on. So I hope that answered your question. What is the equation for bond energy? So with bond energy, I'll just show you here. So that's just for higher students as well. So bond energy, they will always give you bond energy in a table, and you're just calculating. So for example, with CH4, you can see I've got 1, 2, 3, 4 bonds of CH. So I do 4 times 413 there. Remember, molar ratios also affect this. So for example, I've got 2 moles of water here. So I've got 1, 2, 3, 4 OH bonds, which you've got there as well. So remember, molar ratios affects that. In AQA, they don't really penalize you for which way you minus them, but you could just do products minus reactants, and that gives you your net energy release. But just remember, if you've got more energy released, that's an exothermic reaction. So if your products are bigger than your reactants with the energy per mole, then it's an exothermic reaction. Likewise, if it's smaller than the reactants, then it's an endothermic reaction. How do you work out the relative formula mass? In terms of like isotopes, is that what you're referring to, Akib? Or is it just adding? Okay, so yeah, in terms of isotopes, okay, good question. So that's just, that looks horrible, but it's not that bad. So looking at this example here, if you've got chlorine 35 at 75% and chlorine 37 at 35%, these here are just representing the mass numbers of 35 and 37. All you're doing is you're just timesing each of them along. So we've got 35 times 75. We then add that to 37 times 25. If you had a third one, you just add that on. And then you just divide it by 100, because 75% and 25% is 100. And then that gives you your relative atomic mass. Any more questions? What is bond energies? Bond energies is energy required to break that bond or make that bond. They'll always give you them values. You don't need to memorize them. Make sure you also remember the colors of the halogens as well. That's quite common as well. What is activation energy? Activation energy is a minimum amount of energy required to start a reaction. So you can't just leave reactants to actually start. You need the reaction. You need to put energy into it. That energy is the activation energy to start off that reaction. Also, just to note as well, chemistry paper 1 tends to be the highest grade boundaries out of all 3 sciences for paper 1. Does a catalyst decrease activation energy? Yep, a catalyst decreases the activation energy, and it does this by providing a different route for that reaction to happen. And it also speeds up a reaction without getting used up. Strong weak acids, that's probably one of the most complicated topics in here, and it doesn't really get assessed much. But what I would say with strong and weak acids, so I'll just show you in the summary sheet. So it's basically the ability for it to dissociate, which allows it to be a strong or a weak acid. So I would just look at this section here on the summary sheet. All that. Would 62 out of 70 be a grade 9 chemistry paper 1? Honestly, I couldn't say. I would say look at past grade boundaries, but chemistry does tend to be the higher one. A lot of people tend to do well on chemistry compared to the other exams. Right, any more questions, or should we wrap it up there? We've got physics on, I think, Wednesday, so a day before the exam. That should be a good one. But good luck with your exams tomorrow. I hope that was helpful. And I'll get this recording up, and I'll also send you the notes. So is it worth doing the science paper backwards? Not really, because they don't always end with a hard question, if that makes sense. So you can have a look at the question if it makes it easier for you, because they do tend to be a bit harder, but yeah, it is. But yeah, I'll get this video up and I'll also send you the notes as well. But good luck with your exam tomorrow. Wish you all the best. Hope that was helpful. Okay, bye guys.